Thank you very much. So indeed, I'll talk about the Farrell Jones conjecture for mapping class groups. And this is all joined with Mladen Bestvina. And our theorem is the theorem of the title. So let sigma be a closed surface of genius G, maybe with punctures. Then the mapping class group satisfies the Farrell Jones conjecture. And the statement we really prove is slightly different, or is, well, it's different. And to be safe, I put an assumption on the surface, but there are only finitely many that don't satisfy the assumption, and in those cases, the Farrell Jones conjecture is known. So then the action of the mapping class group on the Thurston compactification of Teichmüller space that's what we really study, and that has a certain property that I'm going to call is finitely F amenable, and here where F is a family of subgroups, so it's the family of subgroups of the mapping class group that virtually fixes a point on the compactification of Teichmüller space. Okay, and the goal of the first talk is to explain the statement of theorem B and Y, and maybe motivate the definitions a little bit, and talk about the relation to theorem A. And just in case somebody ventured in here because of the mapping class group in the title and not because of the Farrell Jones conjecture, I want to give a very brief summary or introduction review of the Farrell Jones conjecture. Even though many of you certainly don't need it. Okay, so let R be a ring and G be a group, and the Farrell Jones conjecture is about the K-theory of the group ring, the algebra K-theory, and it informally states that this can be computed in terms of the K-theory of subgroups, of K-theory of group rings of subgroups, where we only have to consider the virtual cyclic subgroups. Okay, so then questions about this are reduced to questions about virtual cyclic subgroups, and sometimes those are then computable, and then you know what this is. Okay, and the similar for L theory. Okay. And of course, Farrell Jones not only made the conjecture, they proved this in many cases. Including pi1 of non-positively curved compact manifolds. And sort of right from the start, they introduced the key methods. In particular, they used the geodesic flow to prove statements in algebraic K-theory. And this is, I mean, nearly all proofs about the Farrell Jones conjecture today still use this, use the version of the geodesic flow. So as we will today, right? So the proof of the mapping class group, in this sense, it's still, you can still see the old proofs of Farrell and Jones in there. Okay, and of course there's interesting applications. And manifold topology, the Barrel conjecture. And the Novikov conjecture, and maybe more important for us today is that it's always often helpful to consider a variant where you work relatively to a bigger family of subgroups than just the virtual cyclics where you want to end up in the end. So you can replace okay, so then of course you get an easier statement, and then you can try to prove inductively, go down from the bigger family to a smaller family of this. Okay, and I think I missed something I wanted to say. Right, so I only gave the statement very informally, but there is one instance that one can give very explicitly easily. So if we have the Farrell Jones conjecture for G, and we know that if we put in the virtual cyclic subgroup, then we don't get any K-theory. So then we compute this in terms of nothing. Then of course we get nothing. Okay, so then right, so this is one way to formulate the Farrell Jones conjecture. And if you do it correctly, then this statement is equivalent to the Farrell Jones conjecture. You just have to be more general about what a ring is. Okay. Okay, so the main goal is now to explain the technical term appearing in the statement of theorem B. And to start with, I want to start with recalling what an amenable action is. So we have a group acting on a space X. Usually one is interested in compact spaces. Said to be amenable if one finds a sequence of maps defined on the space X to some other G space that is a very simple G space So by this I mean the full simplicial complex with vertex set G. Okay, so this is the full simplicial complex on a set G, but then G acts and it becomes a G space. Okay, and the maps should be continuous with respect to the correct topology, which is the weak star topology. Okay, so we want continuous maps such that they play well with the group action. So want to know how to compare applying G before and after F, and we can take the difference, take the one norm in this space, and are interested in how this behaves in the limit. So the maps get more and more equivariant, and this is uniform in X, but pointwise in the group. Okay. Yeah, I think so. But later we're going to make this smaller, and then it will not longer be an issue. Okay. Okay, but since we're going to repeat this, so we're going to summarize this as saying the Fn are almost equivariant. Right, so that's a property of the sequence of maps. I mean, every single map doesn't work with the group, but in the limit they somehow do. But it doesn't mean that there is a limit of the Fn's. Right? I mean, it's just okay. And of course, I mean, this is called amenable if a group acts, or if we consider the action on a of one Fn. I mean, these maps are continuous. You have to put the right topology on this space. Yeah, exactly. I mean, right. Pardon? Sorry. No, right. It's I mean, it's not the other one norm. It's right. I mean, it's the weak star topology. This has as the probability measures on G. But since we're going to make this finite dimensional, and then we can use the other one norm. Okay. Okay, and I was going to say, so if a group acts amenable on a point, then the group is amenable, if and only if. So that this definition generalizes amenability for groups. And there is a nice non-positively curved example, namely the action of the free group on its Cayley graph, which then is a tree. And the maps Fn can be written as follows. So we have a point on the boundary, and we fix the unit as our starting point in the tree, and then this point gives us a geodesic ray, and along the ray we pick up group elements, and the definition is Fn is we just take the first n or n plus 1 group elements. So okay, and you can see that this is that this has this property. So what you need to compare is so if we first apply G, then we're looking at this geodesic. If we first apply Fn and then G, then we look at the geodesic that starts at G rather than E, and we consider this for a long time. So there's a large overlap which makes this difference small. Okay. So then one might ask, I mean, if we're flexible about X, in which, I mean, for which groups do we find such amenable actions? And then it's not difficult, or maybe, yeah, not so difficult to notice that this happens if and only if the action on the Stone-Čech compactification has this property. So this is Stone-Čech compactification, and this property even has a name, or it is various names. One of them is that the group is exact, or maybe it would have been better to, yeah, okay. Or maybe it would have been better to say G is boundary amenable, and then this also implies a different property that's called exactness. Okay. And this, sorry, yeah. I mean, right. The real statement of G is exact is a statement about C star bus that I couldn't tell you what exactly is, but it's equivalent to this one. And this relates to the Farrell Jones conjecture in that it gives not the Farrell Jones conjecture, but something in this direction. So if G is exact, the Novikov conjecture holds for G. And this is due to Nigel Hickson, and I think it builds on work of Go-Yang Yu. Okay. And concerning the mapping class group, I think it means a rational injectivity of the Baum-Kohn map. Yeah. Maybe is Nigel here? No. Integral. With finite subgroups is the proper. Yes. Okay. So okay, it gives the what you just said is it gives the integral injectivity of the Baum-Kohn assembly map for these groups. Okay. And this property is known for the mapping class group by work of Hammenstedt and independent proofs of Hammenstedt and Kida. So the mapping class group is exact. The difference in the statements is that the space Kida considered is bigger. It might have been the Stone-Čech compactification, and Hammenstedt considered a smaller space, so it's a priori a stronger statement. Okay. Maybe I should stop making these lines. Let's see. Okay, but this is still very much something that needs to work in the Baum-Kohn world because we're dealing with infinite dimensional spaces. And now we want to go to finite dimensions. So we're going to consider just the n skeleton. Inside the full simplicial complex. So now we have just measures supported on at most n plus 1 points. And a result of Gantner-Willett and U is the asymptotic dimension of a group is finite if and only if we find almost equivalent maps on the Stone-Čech compactification that take values in this finite dimensional subcomplex. Okay, so this is then clearly considerably stronger. Well, I mean, the requirement is clearly stronger, and we want to end up in this finite dimensional subspace. And but again, this can be done, and that's the result of Bestvina, Bromberg, and Fujiwara. The mapping class group is not only boundary amenable or exact, its asymptotic dimension is finite. Okay, and then one can go back. Maybe. And then as a corollary by Daniel, one gets that the integral Novikov conjecture now in algebraic K-theory and not topological and L theory for the mapping class group. Right, statements like this, if we have finite asymptotic dimension, that there have been statements before, but usually they require a finite co-compact classifying space for the group, which the mapping class group does not have, but it's finite enough for Daniel's result to work. Okay, and this goes via FDC as discussed in other talks. Okay, okay, so this things are getting better. We're in finite. We have a finite dimensional target, but still, what's not good is the Stone-Čech compactification. So the technology for actually proving surjectivity for Farrell Jones requires much nicer spaces than the Stone-Čech compactification. Okay, and this causes a problem. Right, so if we want a nicer space, then there are often fixed point theorems. I mean, Brouwer's fixed point theorem, for example. And as soon as we have fixed points on the space we're acting on, we're obstructed. I mean, those maps are obstructed. We cannot find such maps. So. Yeah, sorry. Maybe then I don't write it. Okay. I just wrote what I said. For nice space, we often have fixed point terms, and now I'm just going to write that fixed points or isotropy groups are a problem. So right. So if the action of G on X has more than just finite isotropy groups, then we cannot get into a finite dimensional space. Basically because if we have an almost equivalent map. What did I say? So finite isotropy is not a problem. The existence of, oh, I said something that I didn't. Okay. That's what you want. Okay. Infinite isotropy of struct, exactly. And the reason is, if we have an infinite subgroup that fixes a point here, then it will, over here, we'll have to almost fix points, but almost better and better. And since we're in finite dimensions, this actually forces the infinite subgroup to actually fix a point. Okay, but on here we cannot have a fixed point for an infinite subgroup. But of course we can have fixed points for finite subgroups, particularly if the order of the subgroup is less than n or n plus 1. Okay, good. So for this reason, now we have to be more generous about the target of our maps. Okay. So okay, so we introduce isotropy to the target of our maps. So we start with some family of subgroups, and then we just replace G by a G set which isotropy, right? And I want isotropy for every group in F, so I can do, for example, this. Just take the disjoint union of these orbits, and then again take first the full simplicial complex, and then the n skeleton. On this set. Okay, and now we can ask, how about almost equivalent maps to something like this? And that turns out to be good for the Farrell Jones conjecture. Okay, but before it does, and I'll state it in a minute. No, I don't. We don't have to actually. We don't have to take a family. We don't have to act on this on here. I mean, it just acts on each one of those. Right? I mean, I could have taken just one from each conjugacy class because then I get enough isotropy already here. Right? I might have just said take any set S such that the isotropy is F. Okay, good. I mean, it's only about. It's not about this particular set. It's just about the isotropy. We just have to get the right isotropy. Okay, so then if we have this, then this is the definition of is N F amenable. Right, so we want a sequence of maps from our space to now this bigger target. And the maps should be almost equivariant. And it's sensible, I mean, if we have X to take for F, at least the isotropy groups for the action of X, or as in our case, the virtually isotropy groups for the action of on X. Okay, and finitely means just if we have this for some n, and we're only interested in finiteness. And just to relate this to things we like. So if X is not a compact space, or not necessarily a compact space, but a space on which the action is very organized, it's a GCW complex with isotropy in F, and finite dimensional, then we find F from X into this gadget even equivariant. Okay, well, I mean, this is close to being the classifying space. Okay, so this definition is sort of saying, okay, we have a space. It's not a GFCW complex, but at least, you know, in some approximate sense, it relates to a GCW complex. Right? It doesn't have an equivalent map as a CW complex would have, but it has a sequence of almost equivalent maps. Okay, but well, I mean, then there's if I take all subgroups, then I have a global fixed point here. And on a global fixed point, I'll always find an equivalent map, right? And then I can just map to this fixed point. So, right. So clearly, the bigger I make the family, the easier it is to find these maps. And yeah, and that's exactly the game we're playing, right? We're trying to make the family big enough that we can get this map, but not too big to get an interesting result. Okay. And together with Wolfgang and Holger, we proved, I mean, we didn't call the condition this, we just wrote it out. But if this condition is satisfied for an action on a sufficiently nice space, then the Farrell Jones conjecture holds. So if G on X is finitely F amenable with X, and now nice means well, it should be a Euclidean retract. For example, and that's the example we're going to need today, a disk, or if we think about the free group, it could be the compactification of a tree. Then now we get the Farrell Jones conjecture relative to this family that we're working relative to. Okay. So, and what we really did here is we studied hyperbolic groups and then just wrote down what our proof for hyperbolic groups needs. Okay, so if G is hyperbolic, then you can take the Gromov compactification of the Rips complex, adding the boundary of the group, and Bestvina and Mess had shown that this is a nice space. It's a contractible, it is a Euclidean retract, in particular it's contractible, and we then checked this condition. Okay. And now we can, it's almost clear what the relation between B and A is. All right, so theorem B implies theorem A. So theorem B was the mapping class group acts finitely F amenable on the Thurston compactification of Teichmüller space, and theorem A was the Farrell Jones conjecture for the mapping class group. So if we have theorem B, then by the result that I just hid here, we get the Farrell Jones conjecture for pardon? No, this is the fine point I'm explaining now. That's the only thing that still needs a little argument, and I'm just going to hint at how it goes. Okay, so the data Farrell Jones conjecture for the mapping class group relative to exactly F. Okay, but then this reduces us to studying the subgroups here in F, but they basically turn out to be mapping class groups themselves, but of smaller complexity. So we can argue by induction. Okay, so in induction, hold on, I'll let me divide and then I repeat. Okay, so let me so B. Right, we studied. This is about the action of the mapping class group on the compactification of Teichmüller space, and we simply took for F virtually fixes a point. Okay, that was just to make the statement of the theorem easy. But then you can go and, I mean, then it's known what these groups are. Okay, and they all are themselves almost mapping class groups of surfaces, of subsurfaces of sigma. In particular, they're sort of easier mapping class groups, and we can argue by induction. Okay, so and this, I mean, this reduces the computation for the mapping class group to those in F, but then for those in F, we can reduce further by the same result applied to the smaller mapping class group, and so on. And then at this point, it's important that, I mean, that you're not talking just about the mapping class group for connected surfaces, because even if you start, for surfaces without boundary, without punctures, even if you do that, then the isotropy groups will involve punctures. So it's better to start with punctures to begin with. Okay, and then you get the Farrell Jones conjecture for the mapping class group itself. Actually, it's, I mean, it's, I don't know what happens for other compactifications, but it might just also work. I mean, I'll explain maybe in the second talk what the Thurston compactification is. I mean, it is a disk. But yeah, I'll give. Well, I mean, I could. Why not? I mean, why not change things a little bit? And give you the Thurston compactification. Because you said you're not going to be here. Sorry? Okay, that's a good point. So the first I said there is finite exceptions, but those are the mapping class group are usually finite or hyperbolic. Okay, but there is, I mean, in this induction, so it's not quite true that those are all mapping class groups themselves, and it's also not true that they're just products of mapping class groups. But they're central extensions by free abelian groups. So the only additional input sort of this needs is that we know the Farrell Jones conjecture for free, well, maybe virtually abelian, virtually free abelian, virtually finite generic free. You know what I mean? Virtually Zn. Okay. This is used here in the induction, and sort of the Zn case. I mean, it sounds kind of easy, but it's difficult. It's not. You cannot get to it from this sort of technology. Right? I mean, there is not the Zn. We don't know that there is an action that's finitely virtually cyclic, amenable on some contractible ER. So the proof from this point of view, the proof for abelian groups is more complicated, and it's used in here. Okay, but it's known, so we're fine. Pardon? Again. Oh, basically by this number that I wrote down that needed to be positive. Right? I mean, or you can make up all sorts of complexities. Right? All you need is that the subsurface of a surface has a lower complexity. And you need to define subsurface correctly. I mean, the ones that appear, right? You don't want to add punctures to make it more complicated. Right? That wouldn't be a subsurface. Okay. Okay, so Teichmüller space is we take our surface, we take out the punctures, and we identify it by homomorphism with a complete hyperbolic finite volume surface. Oops, so this is M. And then we only use the identification up to homotopy. So if an isometry between M and M prime and phi prime are the same up to homotopy with respect to this isometry, then the 2 points in Teichmüller space are the same. And then to get a topology, we look at homotopy classes of essential simple closed curves on our surface, and of course the mapping class group acts on both. Right here, because this was defined on the surface here by changing the identification, changing the marking, and we get, given a curve and a metric, we can measure its length. So we get a map from T times S to the positive numbers, point in Teichmüller space, and the curve is the length of the curve with respect to the Teichmüller space, which means, right, we make we take the shortest curve with respect to this metric. We take the geodesic representing the homotopy class, and from this we get a map from T to R times S for every curve a copy. That's an embedding, and it remains an embedding if we projectivize over here. But then, once we've projectivized, the closure becomes compact, and that's the Thurston compactification. That's what Thurston proved. So Thurston. And the interior of the disk is just Teichmüller space. So none of the closure points were in Teichmüller space to begin with. And the boundary has lots of, at least two descriptions. One of them is as projective measured foliations on the surface, which maybe I don't get into now. Okay? But the boundary has been studied in detail, and lots of things are known, and there are lots of descriptions what points are. Right? So